So Calc 1, Lecture 3. So any questions before we start?
Do you also have the date for the midterm?
Yes and no. So just 1 second. The midterm will be when? It will be approximately March 15th, but within a week or so of that, one way or the other, depending on how far we get. But it's roughly the middle of March. But I don't have the exact date yet.
Okay, thank you.
Yep. Okay. So we did a little pre-calculus review. We talked about limits, and I want to continue to talk about them because they are very, very, very important in mathematics. So let's just begin to say something about limits. We have a function y equals f of x, which is certainly defined for all x near some point x equal a. And we have this notion of saying that the limit as x approaches a of the function f of x. So this sort of complicated symbol means the limit as x approaches a of f of x. We then say that's equal to a number L. So in a somewhat imprecise sense, that means f of x is arbitrarily close to L for all x that are close to a. So suppose we have a function and the graph of the function looks something like this. So this is a, and this is the graph y equals f of x. And you can see that as x gets closer and closer to a from the left or from the right, the function f of x is getting closer and closer to this number f of a. So the way I've drawn this example, the limit of f of x is x equal a, as x approaches a is equal to just f of a. But to take a somewhat more complicated example, suppose we take a function that looks like this. Let's say it's equal to so f of x is equal to x for x not equal to 2. And maybe it's equal to 1 when x equals 2. So this is a sort of a function which has this sort of the following shape. 0, 1, 2, 3, and so on. As x approaches 2, you're moving up along this curve. As x approaches 2 from the left, as x approaches 2 from the right, you're moving down the curve. And as you get closer and closer to 2, the function f of x is also getting closer to 2. But the value of the function at x equal 2 is 1. So this function has a kind of a jump. But even though, so in this case, the limit of f of x as x approaches 2 is equal to 2, right? You're getting closer and closer to 2 as you approach x, which is not f of a, not f of 2, right? So the limit of a function at a point is not necessarily the value at the point, because you could have a kind of a jump or something weird like that. That's what happens. So sometimes it's better to understand things by seeing when they don't happen. Suppose we have another function, which is f of x is equal to, let's say equal to 1 for x less than 2, and it's equal to 3 for x greater than or equal to 2. So what does this function look like? When x is less than 2, the function is equal to 1. And when x is greater than or equal to 2, the function
Anche son vulnerables. Señores,
is equal to 3.
vamos a ver mucho.
Okay. So this function looks like this. It's the horizontal line y equal 1 as you approach 2. But when you get to 2, it jumps to 3. And at x equal 2, it's equal to 3. And then it's 3 everywhere after that. So this is how you would write this function in mathematical language. And what will we say is the limit of f of x as x approaches 2? Well, if you approach 2 from the left, function is equal to 1. But as you approach 2 from the right, the function is 3. So there's no single number that f of x gets close to as you approach 2. So for this, we would say this limit does not exist. That limit doesn't exist. So limits of even simply defined functions don't necessarily exist. Let's look at another example of the same type. Suppose we take the function f of x, say f of x is equal to x minus 1 if x is less than or equal to 3, and x plus 1 if x is greater than 3. So what is the graph of such a function look like? So here's x equal 3. That's the line x equal 3. When x is less than or equal to 3, the function is x minus 1. So you know from pre-calculus, this is a straight line with the y-intercept equal to 1 and slope y-intercept minus 1 and slope 1. So this is the point 3, 2. But for x bigger than 3, f of x is x plus 1. That's a line with slope 1 and y-intercept plus 1. So when x is equal to getting close to 3, this is the point 3, 4. So this is a function whose graph has a jump in it. It's like you start out at minus infinity and you're moving up this line until you get to 3. But once you get 3, you jump. And then for x bigger than 3, f of x is x plus 2. So again, for this function, the limit of f of x as x approaches 3 does not exist. Because there's not a single number that the function is close to when you're near 3. On the other hand, if you only consider numbers less than 3, this function does have a limit. And if you only consider numbers greater than 3, the function also has a limit, but they're different. So these are what are called one-sided limits instead of two-sided limits. So a one-sided limit, let's say you're coming from the right, the limit for this function f of x, as x approaches 3, and I'll put a plus sign of it, that means for numbers that are bigger than 3. So as you're approaching 3 from the right, the function is moving down this line and it's approaching the number 4. You're getting closer and closer to 4 as you approach 3 from the right. But as you approach 3 from the left, you're approaching the number 2. So this function has one-sided limits, but it doesn't have a two-sided limit or an ordinary limit. Okay. The limits can be very interesting. So suppose we define a function for x greater than 0. Suppose we let f of x be the function cosine of 1 over x. Now you have to know the graph of the cosine. Graph of the cosine looks like this. This is y equal cosine x. So it goes from -1 to 1. At x equals 0, it's 1. And at 2 pi, it's 1. And it just oscillates like this. That's the graph of the cosine. But the graph of 1 over the cosine is completely different. So as x approaches 0, 1 over x, what does 1 over x look like? If you look at the graph of the function y equals 1 over x, it looks like this. As you approach 0 from the right, 1 over x is going to infinity. So 1 over x is going to plus infinity as you approach 0 from the right. And what does the graph of y equals the cosine of 1 over x look like? Well, it starts out oscillating slowly, but oscillates faster and faster and faster. There's a very good picture of this in your book on page 67. And this function, the limit of cosine of 1 over x, as x approaches 0, I'll just write dne, for it does not exist. Right? You're getting closer and closer, in fact, to every point on the y-axis between -1 and 1. There's no single limit. Any questions about this, or any questions about any of the homework problems or exercises in the book that you've seen? So it's important to know that for simple functions, it's easy to calculate a limit. So suppose we have a linear function. So that's y is equal to what function of x? mx plus b. It's just the line with y-intercept b and slope m. And if you take any point A on the real line, the limit of f of x as x approaches A, that's the same as saying the limit as x approaches A of mx plus b. Well, as x gets closer to a, mx gets closer to ma, mx plus b gets closer to ma plus b. We just get ma plus b, which is in fact the value of the function at a. So that's very simple. And on Monday, I reviewed, or I listed, some of the so-called limit laws. So if you know the limits of two functions, you know the limit of their sum, difference, product, and quotient, and so forth. So for example, for the sum of two functions, the limit of f of x plus g of x as x approaches a, if both limits exist, this limit is just the sum of the limits. Actually, I shouldn't write it like this. If both of these limits exist, the limit of the sum is the sum of the limits. And the same is true for the difference. If I put a minus sign instead of a plus sign, the limit of the difference of two functions is the difference of the limits. And the same for products. The limit of f of x times g of x as x approaches a, if both limits exist, is the product of the limits. And the same for quotients. If I take f of x divided by g of x as x approaches a, this is the limit of f of x as x approaches a divided by the limit of g of x as x approaches a, if this quotient is not zero. You can't divide by zero, but if the limit of g of x is not zero and the limit of f of x exists also, the limit of the quotient of two functions is the quotient of the limits. And we can write the analogous facts down for powers and for roots. But then this immediately tells us how to compute the limit of a polynomial or a rational function. So in
Professor.
the text, you find the following example.
Professor,
Yes,
could you go back to the previous page, please?
sure.
A little bit down. Yeah, thank you.
Again, these are all in the book on page 72, right? And the difference between my lecture and the book is you can read the book, but you can't read my handwriting very well. Okay. So suppose we have a polynomial, let's say a cubic, degree 3, 7x cubed plus 3x squared plus 4x plus 2. And we want to find the limit as x approaches some number a of p of x. So let me just write this down in detail so you get an idea of what this means. So this is the limit as x approaches a, and this is my polynomial, 7x cubed plus 3x squared plus 4x plus 2. But the limit of a sum is the sum of the limits. So that's the limit of 7x cubed as x approaches a, plus the limit of 3x squared as x approaches a, plus the limit of 4x as x approaches a, plus the limit of the constant function 2 as x approaches a. Or maybe I'll just follow the text in this regard. The limit of 7x cubed, 3x squared, and the linear function 4x plus 2. So for a constant multiple, you can always take the constant outside, right? One of the limit laws is the limit of c times f of x as x approaches a. If c is a constant, it's just c times the limit of f of x as x approaches a. So here I take a equal to 7. I can take this outside. This is 7 times the limit as x approaches a of x cubed, plus 3 times the limit as x approaches a of x squared, plus the limit of 4x plus 2 as x approaches a. Now, the limit of a product is the product of a limit. The limit of a power is the power of a limit. So the limit of x to the power 3 is the limit of x as x approaches a cubed. And the limit of x to the power 2 as x approaches a is the limit of x as x approaches a squared, plus this. And the limit of x approaches a of x is just a, so this is 7a cubed. The limit of as x approaches a of x, so this is a, so this is 3a squared. And for a linear function, we already saw the limit as x approaches a is 4a plus 2. And if you compare this to the original polynomial, this is just the polynomial p evaluated at a. So this is an instance of the following fact. For every polynomial p of x, the limit as x approaches a of p of x is just the value of the polynomial at a. And using the quotient rule, for every rational function, a rational function is a quotient of polynomials, p of x divided by q of x, with q of a not 0, the limit as x approaches a of p of x over q of x, the limit of a quotient is the quotient of the limits. And these are polynomials, so this is p of a divided by q of a. Okay. Okay, I also mentioned on Monday what is called the squeeze theorem. So suppose we have some problem, we have a function g of x, and we want to find the limit of g of x as x approaches a. That's our problem. And it's a hard problem sometimes. We can't figure it out. But sometimes, if we're lucky, we notice something. So here's my function y equals g of x. This is x equal to a. And we want to find the limit of g of x as x approaches a. So for example, suppose g of x is equal to x squared times the sine of 1 over x. This is a very, very, very complicated function. And say we want to find the limit as x approaches 0 of g of x. I mean, first of all, you have to notice you can't even plug x equals 0 into this. Oops. You can't plug x equals 0 into this because 1 over 0 isn't defined. So this function's not defined for x equals 0. This is only defined for x different from 0. But sometimes it happens when you have a function g of x that there's some other function, let's call it y equals h of x, and suppose that h of x is bigger than h of x when x is close to a. So for x near a, my function h of x is bigger than g of x. And suppose I have another function, y equals f of x, which for x near a, f of x is greater than or equal to, is less than or equal to g of x. So g of x, see, where's my function g of x? That's the g of x. G of x is squeezed between f of x and h of x. F of x is below, h of x is bigger, is above. But if the limit of f of x as x approaches a and the limit of f of h of x as x approaches a exist and equal to some number L, then this function that's squeezed in between them has the same limit. The limit as x approaches a of g of x is also equal to L. So if this red function is squeezed between f and h, and as you approach a, f approaches some number L and h approaches some number L, this function squeezed between them has to approach the same limit. Okay. Any questions about this? So this is, again, in a sense, a kind of review, because we discussed this on Monday, and I'm trying to go through this again slowly. And so I only can keep going forward, or I stop if you have a question, but if there's no question, we continue. So let's look at this example, the function x squared sine of 1 over x. So suppose I have the function g of x equals x squared times the sine of 1 over x. And I'm interested in the limit as x goes to 0 of g of x. So what we know about the sine is that for any x different from 0, theta, let's say theta be 1 over x, sine of theta, or the sine of 1 over x, again, you have to know what the sine function looks like. It looks like that. It oscillates up and down between -1 and +1. So this is always between +1 and -1 for all x. So that is for all x not equal to 0, the sine of 1 over x is between 1 and -1. So if I multiply by x squared, minus x squared is less than or equal to x squared times the sine of 1 over x is less than or equal to x squared. So this is my function, g of x. Think of this as h of x, and this is f of x. H of x is x squared. It's the parabola. F of x equal minus x squared is the parabola opening down. And my function g of x is always in between them. I don't know what it looks like exactly, but it's in between them. This is g of x. And as x approaches 0, x squared approaches 0 and minus x squared approaches 0. So the limit of this g of x as x approaches 0 is the same as the limit as x approaches 0 of x squared, and the same as the limit as x approaches 0 of minus x squared. And both of these is equal to 0. So this complicated function g of x is squeezed between these two parabolas. And these both approach 0 as x approaches 0. So g of x has to approach 0 as x approaches 0. Right? That's an example of the squeeze function in operation. And again, I'm trying to pick examples that are in the book, so it's very easy to follow when you're studying at home. And yeah. Now, the book chooses to use the theorem to discuss some trigonometric limits. So let's look at the function sine of x. So everyone knows, in the sense that it certainly is part of pre-calculus, which is prerequisite. So this is minus 2 pi minus pi 0 pi 2 pi 1 and minus 1. Sine of 0 is 0. Sine of pi is 0. Sine of 2 pi is 0. And we have this oscillating function. Looks like this. This is the graph of y equals sine of x. And the limit of sine x as x approaches 0 is 0. You take y equals the cosine of x. This also goes from -1 to 1. At 0, the cosine is 1. At pi, the cosine is -1. At 2 pi, the cosine is 1 again. At minus pi, the cosine is -1. At minus 2 pi, the cosine is +1. And at 0, at multiples of pi over 2. So the graph of this function, the cosine, looks like this. And the limit of the cosine of x as x approaches 0 is equal to 1. So using these facts and what has to be your knowledge of trigonometry, again, with all these things, if you ask me a question, I'm happy to answer it, but it's your responsibility if you don't remember the trig from pre-calculus to go back and review it yourself. Again, if you have a question, I'm happy to answer it for you. So here's example 10 in the book. Calculate the limit as x goes to 0 of sine squared x over 1 minus cosine x. Now, you can't just plug in x equals 0 because sine of 0 is 0, cosine of 0 is 1, 1 minus 1 is 0. If you just try to plug in x equals 0, you will get 0 over 0, which isn't defined. So to solve this, compute this limit, you have to try something else. And one of the most important, perhaps the most important identity in trig is sine squared x plus cosine squared x equals 1 for all x. So here I have sine squared x. This is the same as saying sine squared x is 1 minus cosine squared x. And this factors. This is 1 minus cosine x, 1 plus cosine x. Because one of the factorization theorems, the simplest one, the most basic one, is that you can factor, let's say 1 minus a squared is 1 minus a times 1 plus a. So in calculus, we use this all the time. You have to have this, you have to know this. So I can replace sine squared x by this expression. So this is the limit as x goes to 0 of 1 minus cosine x over 1 plus cosine x divided by 1 minus cosine x. And now you can see a miracle happens. The 1 minus cosine x in the denominator cancels the 1 minus cosine x in the numerator. So this is exactly the limit as x goes to 0 of 1 plus cosine x. And as x goes to 0, the limit of the cosine is 1. So this limit is 1 plus 1 or 2. And that is the answer. This limit that we're trying to calculate is equal to 2. So I would just pause for a minute and encourage you to look over this argument. And if you have a question about any of the steps, to ask me, okay? Sine squared is 1 minus cosine squared, which factors 1 minus cosine x, 1 plus cosine x. You plug that into the limit we're trying to find, sine squared x, 1 minus cosine times 1 plus cosine, divided by 1 minus cosine. So these cancel. And you're left with just 1 plus cosine x. And as x goes to 0, 1 goes to 1, and cosine x goes to 0, and 1 plus 1 is 2. And that's the answer. Okay, any questions about this?
I have a question.
Yes.
How did that cosine x turn into a 1?
So back here, I graphed the function y equal cosine x, okay? That's the that's the graph of y equal cosine x. And as x approaches 0, the cosine x has the limit 1. All right. That's what that says. The limit as x goes to 0 is equal to 1. So here, this becomes the limit of 1 plus cosine x. So by the addition rule for limits, this is the limit as x goes to 0 of 1, plus the limit as x goes to 0 of cosine x. The limit of this constant function 1 is 1. The limit of the cosine of x is 1. 1 plus 1 is 2. That's how we got it. Any other questions? No, okay, good. All right, here's another example of a trigonometric limit. We want to find the limit as x goes to 0 of 1 minus the cosine of 2x over sine x. And again, if you simply plugged in x equals 0, you would get 0 in the denominator. Sine 0 is 0. When x is 0, 2x is 0. Cosine of 0 is 1. 1 minus 1 is 0. So if you just try to plug x equals 0 into this expression, you would get 0 over 0, which has no meaning. It's meaningless. You can't do anything. You need another way to solve this problem. So you look at this and you see here is cosine of 2x. And you have a trig identity, which you have to know, right? The cosine of 2x for any angle x is cosine squared x minus sine squared x. This is the double angle formula for the cosine. Just like the double angle formula for the sine says the sine of 2x is 2 times the sine of x times the cosine of x. But this is the one we have to use now. Cosine of 2x is cosine squared minus sine squared. So 1 minus the cosine of 2x is 1 minus this expression, cosine squared x minus sine squared x. Which if I just expand this, this is 1 minus cosine squared x, and minus times minus is plus sine squared x. And 1 minus cosine squared x, remember, sine squared x plus cosine squared x is 1. So 1 minus cosine squared x is sine squared x. So this is equal to sine squared x plus sine squared x, which is 2 sine squared x. So 1 minus cosine of 2x can be rewritten as 2 sine squared x. So this is my original problem. Compute this limit. The limit as x goes to 0 of this quotient, the denominator is sine x, the numerator is 1 minus cosine 2x, which by this algebraic and trigonometric manipulation is the same as 2 sine squared x. And sine squared over sine x, we can cancel with sine x. This is the limit as x goes to 0 of 2 sine x. And as x goes to 0, sine x goes to 0. So this limit is equal to 0. And that's the solution to the problem. So again, I want to pause for a minute and look that over. And these kinds of algebraic manipulations you're expected to learn and master and be able to do in Math 175. And when you take the midterm on the final exam, you'll have to solve these kinds of problems. Okay. So take a look at that. Any questions about this? Okay, so let's go on a little bit. So we also have the following type of situation. Suppose we have the function f of x equal to 1 over x squared. So this is not defined when the denominator is 0. This is only defined for x equals 0. What does the graph of this function look like? First of all, it's 1 over a square, so it's always positive. It's never equal to 0, and it's never below the x-axis. As you approach plus or minus infinity, this denominator is getting bigger and bigger and bigger. Function is going to 0. But as you approach 0, the denominator is going to 0. This function is going to infinity. And the graph of the function looks like this. And you can have what is called an infinite limit. If I wanted to look at this function 1 over x squared and take the limit as x goes to 0, whether I approach 0 from the left or from the right, this function is shooting up, and we say this limit of 1 over x squared is infinity. It is infinite. So we have, this is an example of an infinite limit. And in fact, the vertical line, x equals 0, that's this line, is what is called a vertical asymptote. That means as x gets closer and closer to 0 from the left or the right, the curve is approaching this vertical line, never touches it, but it gets closer and closer and closer as you get closer and closer to 0. So this is an example of what is called a vertical asymptote. And if you have a function that might look like this, so this turns out to be the graph of a function g of x equal to x minus 2 over x minus 1 squared, x minus 3. So this looks somewhat complicated, but when x is equal to 2, of course, this is 0. As you approach 1 from either side, this is going to 0. So the function is going to infinity. As you approach 3, from the left, these are positive and this is negative. You're going to minus infinity. And as you approach 3 from the right, you're going to plus infinity. So for this function, the limit of g of x as x approaches 1 is infinite. So the line x equal 1 is another vertical asymptote. If I ask about the limit of this function g of x as x approaches 3, that doesn't have a limit, because as you approach 3 from the right, the function is shooting up to plus infinity. But as you approach 3 from the left, the function is shooting down to minus infinity. But what you can say is that this has one-sided limits. As you approach 3 from the right, this limit is infinity. As x approaches 3 from the left, you're going down to minus infinity. And the line x equal 3 is also a vertical asymptote for this function. So these are one-sided infinite limits. So these are examples of when x approaches some fixed number, the limit is plus or minus infinity. But if we go back and we look at our same function, y equals 1 over x squared, there's also the notion of the limit at infinity. We can ask about the limit. Let's call this function f of x. Well, that's the limit of 1 over x squared as x goes to plus infinity. Well, as you approach plus infinity, this function is decaying and approaches 0. So at infinity, this function has the limit equal to 0. And what happens when you go to minus infinity? The limit as x goes to minus infinity is also equal to 0. You're approaching 0 as you go off to infinity to the left. So those are limits at infinity. You can also say these limits don't exist, but, well, sorry, but they do. Yeah. So it's very useful to be able to estimate limits and to find vertical asymptotes. Suppose we had something like this. The limit as x goes to 0 of the function 5 plus x over x. Let's say as x goes to 0 from the right. So this is not defined when the denominator is 0, but when x is positive, this is some quotient of positive numbers. What is this? Well, this is the limit as x goes to 0 of 5 over x plus x over x plus 1. And as x goes to 0, 5 over x goes to infinity, and 1 is just 1. It's insignificant. This is going to be plus infinity. So when x is positive, this is positive, and this is going to infinity. It's going to plus infinity. If I looked at the same function, 5 plus x over x, I wanted the limit as x goes to 0 from the left. That's the limit as x goes from 0 to the left of 5 over x plus 1. That's just a little bit of algebra. If x is negative, 5 over x is negative. And this is getting bigger and bigger in absolute value. So this is going to minus infinity. This is going to be, this is an infinite limit, but it's minus infinity. And for this function, what is the limit of 5 plus x over x as x goes to infinity? That's the limit as x goes to infinity, 5 over x plus 1. As x goes to infinity, 5 over x goes to 0, and 1 is just 1. So this limit is equal to 1. And in fact, if you were to graph this function, you have a horizontal line, y equal 1. And the graph for this function looks something like this. As you go to plus or minus infinity, the limit is 1. You have a horizontal asymptote at y equal 1 and a vertical asymptote at x equals 0. So I'm sure this is a new mode of thinking. You haven't done anything like this before, and most likely in pre-calculus or any other part of high school math. But this is what we are learning in Calc 1 now. This kind of analysis of functions to figure out limits, especially as you approach plus or minus infinity. So here are a couple more examples. Suppose I take the function 2 minus 5x over x minus 3, and I want to know what is the limit as x approaches 3 from the right. So this means I choose values of x getting closer and closer to 3, but always bigger than 3. So if x approaches 3 from the right, x minus 3 is always positive. So this is some positive number, and it's going to 0 as x gets closer and closer to 3. What about the numerator? The numerator is 2 minus 5x. And the limit of that as x approaches 3 is 2 minus 5 times 3, or 2 minus 15, or minus 13. So as x approaches 3 from the right, this is approaching some finite number, minus 13, and this is positive and getting smaller and smaller and smaller. So this is minus 13 times something going to infinity. Sorry, this is going, x is going to infinity. So this is minus infinity. Right? This is always going, as x approaches 3 from the right, this is always negative. This is a negative number over a positive number, so it's negative. And this is bounded, this is getting 2 minus 5x minus 13. This is getting closer and closer to some fixed negative number, while this is going to 0. So the whole thing is going to minus infinity. And if you had the same problem, but now as x approaches 3 from the left, two minus 5x again, as x approaches 3, is going to minus 13. X minus 3 is going to minus, it's going to 0, but it's negative. So 1 over x minus 3 is going to minus infinity, And if you multiply that by some negative number, you get something going to plus infinity. Negative over negative is positive. So this limit is going to be plus infinity. So this, I agree, is complicated. You have to begin to understand this a little bit. So as x approaches 3, 2 minus 5x, it's approaching minus 13. This is always going to be very close to minus 13. It's going to be negative. But x minus 3 is going to 0. So this is going to plus or minus infinity. If 1 over x minus 3 is going to plus infinity, if you multiply it by something negative, it's going to minus infinity. And if x minus 3 is negative and going to 0, this is going to minus infinity. And minus times minus is plus. You get plus infinity. And this, I have to admit, is something you really need to study hard and think about. Right? It's this takes a bit of work. So we mentioned vertical asymptotes, and I also mentioned, but without saying very carefully, what is a horizontal asymptote. So if the limit of f of x as x goes to either plus or minus infinity is equal to some number b, then we say f of x has a horizontal asymptote, or the line y equal b is a horizontal asymptote for the function. So suppose your function, whatever it looks like, it can be very complicated, but as x goes to infinity, the limit of f of x is equal to b. That means that as you go to infinity, the graph of the function is getting closer and closer to this horizontal line, y equal b. And it doesn't matter whether you're talking about the positive direction or the negative direction, whether you're going to plus infinity or minus infinity. We have this idea of a horizontal asymptote. So, or if I use the notation of the book, if the limit of f of x as x goes to infinity is equal to L, then the horizontal line y equal L is a horizontal asymptote. Okay, well, I don't want to push ahead too fast, certainly, and I'm going to talk a lot more about limits next week, really all of next week. And we will end up with a very precise definition of a limit. But I very much encourage you to spend as much as time possible studying the book and doing the homework problems on MyLab, and to keep working at them until you get every problem answered correctly. It's not enough just to have the right answer, which you can find somewhere or other, or where someone tells you, but in order to understand what's going on, you need to be able to actually solve these problems, and the MyLab system is very good for that. So the more time you can spend studying the book, thinking about limits and working problems, the better prepared you will be for the midterm and the final, which is where most of your grade comes from. Okay. Any questions about any of this before? Otherwise, we'll quit. I have office hours Monday, Wednesdays, and Fridays. Today is Wednesday. There's an office hour or problem session at 1 o'clock, and Friday morning at 11 o'clock. And as I always like to repeat, if you have a question and you're not able to come at one of those problem sessions that's scheduled, send me an email and we can work out a time on Zoom where I can log on and you can log in and ask questions. Okay. Anything before we stop for the day? Okay. All right, be well all. See you on Monday.
Thank
This
you,
will be-
Professor.
This will be posted on Blackboard very soon. Sorry, not on Blackboard, on YouTube. Okay, bye all.